Hello, my name is Rajnandini and I'm in 8th grade at Mildred E. Strang Middle School. This is my project on the duality of light, wave or particle.
The quantum world is based on how something can be in two states at once. A good way to help explain this is Schrodinger's cat, a thought experiment that states that if a cat is placed in a box with something that could kill it, you wouldn't know if it was dead or alive until you reopened the box, making it a blur of probability. It can be said, then, that it is both dead and alive. Similarly, quantum particles can spin both up and down and be in many possible positions at once. Light also has a dual nature, where it acts like a wave and a particle. The double-slit experiment showed that when electrons were shot through two slits at once, they formed an interference pattern, like a wave, instead of forming two concentrated lines, like a particle. When light of a certain wavelength is shot at a metal, electrons are emitted from the metal. The photoelectric effect shows that as the frequency of the light increases, the electrons emitted also increase. These are my problem statements, and my goals were to understand why light behaves this way and to observe its dual nature. I hypothesized that light is a wave since we can't see any particle-like properties in everyday life. So, I decided to test this out for myself by recreating the double-slit experiment. I created the double slit by making it right over the laser, using wire and tape on either side. I also used a lens to magnify the results and make them more visible. I tested the lens at different distances from the end of the box to find what worked best. This is a model of my experiment that shows the interference pattern. We made this using the materials we talked about before. I also tested the double slit on a separate piece of paper, but that didn't work well. The laser in my experiment also formed an interference pattern, like in Young's experiment. In Young's experiment, individual electrons also somehow traveled like a wave and formed the same interference pattern. In fact, all particles, not just electrons, act like waves. Why don't we show wave-like behavior then? We'll find out in a few minutes. The photoelectric effect showed light's behavior as a particle. When the intensity of the light was increased, it displaced more electrons but with the same kinetic energy. When the frequency of the light was increased, however, it displaced electrons with each electron having more kinetic energy. This shows that light delivers energy in packets, like a particle. So, back to our previous question, why don't we see this behavior in our lives? Well, as mass increases, the wavelength decreases. De Broglie believed that electrons could behave like waves too, and figured out what that wavelength would be. And this is actually true for all particles. Since momentum is mass times velocity, as the mass increases, the overall momentum will increase, resulting in a decrease in the wavelength, making it so minuscule that we can't observe it. We are much bigger than atoms after all. My hypothesis was refuted since it turned out light is both a wave and a particle. Young's experiment and the de Broglie formula show light's wave behavior, while the photoelectric effect shows particle behavior. Light and the quantum world are very different from our observable world. Another way to look at quantum behavior of particles is through wave functions, which display the probability of a particle being in a particular position at a time. Since quantum computers use superposition and entanglement to compute, we could investigate the duality of photons and how it can be used to improve these computers. Further research in teleportation of objects is also imminent. Scientists have already managed to teleport qubits and photons. Could we find out why electrons in Young's experiment act like particles again as soon as they're observed with flashes of light? This phenomenon is still a mystery to scientists. Researchers are also trying to use light to carry quantum information. These were my references. Thank you.